Let's get going. Here's the first problem. Matt deposits a check for $234.95, this is where the decimals come in, into his checking account. And now he has a total of $1,479.87. How much was in his account before the deposit? Let's look for the information. We're given that he deposits a check for $234.95, and he now has the total of $1,479.87, and we're asked how much was in the account before the deposit. Let's review the information. There's what we're given, what the deposit was and what the present total is. And here's what we're asked. What was the balance before the deposit? It's always useful if you want to think in pictures and to make some kind of a diagram. I always do this because when I can picture something in my head, when I can see it, when I can diagram it, it makes it easier for me to go on and solve it. So let's take a look at the diagram I might come up with. A very simple thing. There's how much he has now, and we show the check, and what we want to know is, what the question mark says is, how much did he have before that check was cashed? We're going to call what he had before the check was cashed with the variable b, the unknown b, and so b plus the amount of the check equals how much he has now. We have this in the form of an equation, and of course we need to try to get b by itself. In order to do this, we subtract 234.95 from both sides of that equation. Let's do that mathematics. B is equal to 7 minus 5 is 2. 8 minus 9 I can't do right away, of course, so I borrow a 1 from the 9. 18 minus 9 is 9. Having borrowed the 1, 8 minus 4 is 4. Notice I put the decimal point directly down in line. 7 minus 3 is 4. 4 minus 2. You're getting good at that by now, I'll bet. And we carry down the 1. So we find that Matt had $1,244.92 before he made the deposit. And of course we can check this by taking the deposit plus the amount before the deposit, adding that to what we get as the solution, and we find we wind up with the amount he had before the deposit, the amount he had after he made the deposit. So we're pretty sure that we've done this problem correctly. Let's look at another one also involving money, but possibly a tiny bit more complicated. And this is something that faces all of us because when we get our bank statement back, it doesn't account for all of the checks we might have outstanding. So we think, wow, we have a lot of money here. But you need to remember that if you have checks out there that haven't been cashed, you have to account for them. And that's what this problem deals with. Stan compares his checkbook record with his monthly bank statement, which says he has $876.47. But he sees, by looking at his statement, that checks for $32.84, $97.10, and $158.78 haven't been cashed yet. And so we'd like to know how much money Stan really has available. Let's look for the information again. He has $876.47. That's what they said he has, but he finds there are checks that haven't been cashed. What we want to know is how much money does he really have available at this point. Let's summarize the information. There's his bank balance statement, but there are some uncashed checks, checks that are not that he knows he's written, that aren't included in that balance. And we'd like to know what's really available. There's our diagram. The amount available is going to be whatever the total is, but you need to take into account there are those checks that are floating around out there, and you never know when they're going to get cashed, so you have to be careful. So the amount he really has available is the balance minus those uncashed checks. Let's work on that. There are the uncashed checks are going to be 158, 78, 97, 10, and 3284. So we need to get the total, the sum of all of those uncashed checks. And when I do the math, I find that there is a total of 288.72. The total available then is the balance minus those checks that are out in the system. When I do the math, I find out then he really, honest to God, has available to use $587.75. Let's check this. We know that the balance is going to be what's available plus whatever is uncashed. So we go the other way now, and we've calculated by doing the problem that what's available is $587.75. We add to that the total of the uncashed checks and want to see whether or not that's going to balance. And in fact, it does. So we're pretty sure that we've done this problem correctly. Let's look at another one similar, again involving money. When you're dealing with the decimal system, money always comes to the forefront because, of course, our money is based on the decimal system. Let's take a look at this problem. And this is fairly common. In an ad for a computer system, it lists the price as $899.95. There's an instant rebate of $55.55 and a mail-in rebate, you're lucky if you ever see that one, of $66.66. We'd like to know the final price of that system after both of those rebates. We look for the information. The list price is $899.95, and we see there are two rebates. And what we'd like to know is the final price after those rebates. Here we go. We summarize the information. Original price, $899.95. Couple of rebates. At least you know you're always going to get the instant rebate. It's always a gamble on those mail-in rebates. My own luck on those things have been about 50-50. Well, it's worth a try. Anyway, the final question is, what's the final price of the computer system? We make the same kind of diagram we made before. There's what the system lists for. I show the two rebates, and we look at the final price. So we see that the rebates plus the final price will be ultimately what that system lists for. A little strategy there. So we analyze this. We'll let F be the final price of the system. If I take the final price, add in the two rebates, I get what the system sells for. Now I have this in the form of an equation, and I can begin to solve the equation. The first thing, of course, is to simplify. I have on the side with the unknown two numbers, and of course I can add those numbers together as decimals. Straightforward addition. Just remember you need to line up the decimal points. Now that I have that, I have this equation. And remember, as we've done a lot before, I need to get the final price, the variable f, by itself on one side of the equation by performing legal operations. In this case, I want to subtract $122.21, the sum of both rebates, from both sides of the equation. When I do that, I find that the final price is $777.74. So that's what that system I'm going to buy will ultimately cost me if, if I get that mail-in rebate back. It's always a big if. Let's check this. With a final cost, which we calculated, plus the rebates, have to be the original price. So we take the $777.74 that was the result of our calculation, add the sum of the rebates, and see if, in fact, that works out. And I probably would hesitate to do an incorrect problem for you here. So sure enough, that's going to work okay. Of course, if this didn't work out, what I would have to do is go back and find where I might have made a math error. For example, I could have added the two rebates incorrectly. I might have done something slightly wrong, so checking is always a good idea. And of course, it's a good idea right away. You can always check to see whether your answer is reasonable. If I found out that the final cost, for example, was more than the original price after the rebates, I would be suspicious. Maybe I added instead of subtracting. Always look not only to see if your final answer checks mathematically, but it's always good to ask when you're doing any kind of word problems about the reasonableness of your answer, insofar as you can tell. Sometimes the numbers you're dealing with are not anything that's in your experience and makes it hard to estimate. But if it is, please check for reasonableness. Let's go on and look at something possibly a little more interesting. We're going to deal now with word problems with two unknowns. And here's where you have two separate things you're looking for that you need to find a relation for in order to be able to solve the problem. Let's take a look at the first problem. Amy receives $22.25 an hour for up to 40 hours per week, her regular salary, and then overtime is paid at $37.80 an hour. We're given how much she receives in her paycheck, $1,173.50, and we'd like to know how much time she worked that week. And there's another little caveat there. Typically, you don't talk about decimal time. For example, if I worked 87.37 hours, you don't often talk about time in terms of decimal parts of an hour. You talk about it in terms of minutes. So in this case, we're also going to ask to take the decimal part of whatever we get, if there is one, and change it to minutes. So we report our final answer here in hours and minutes, not hours and tenths or hundredths of hours. With that introduction, let's take a look at the problem itself. At work, Amy receives $22.25 per hour for up to 40 hours a week, her regular salary. Then any time beyond that is paid overtime at a very nice rate of $37.80 per hour. If she receives $1,173.50 in her paycheck, we'd like to know how much time she worked that week. And in particular, we'd like to express the time in hours and minutes. So we're going to have to do a little additional calculation, also involving decimals. Let's look for the information we're given. We see that normally she gets $22.25 an hour for up to 40 hours, and a higher rate beyond that. We're given how much she gets in her paycheck, and we're asked how much time she worked that week, and we're told that we need to express that in hours and minutes. So here's the summary of what we're given, and we're asked how many hours she worked. Again, it's always good to make a diagram. There's the 40 hours at $22.50 an hour. And then however many hours at $37.80, and we want to know X, the total time. So let's try analyzing this. X is going to be the total number of hours she works. There's what she does normally. She works 40 hours at $22.50. The rest, and that's what we need to express mathematically, is $37.80. Well, the rest is going to be X, the total number of hours, minus the 40 we already know she worked at $22.50. Then we can write the equation that her total pay is the 40 hours of pay plus the overtime pay. Let's see how we'll calculate that. Remember that the total pay is going to be the number of hours times the hourly rate. Let's write that in that way. There's the total. That's the total she got, the 40 hours times the $22.50 an hour, the hourly rate for the up to 40 hours. Then we add in the number of hours, x minus 40, she worked beyond the 40 hours, times the rate for that overtime. Now we have an equation we can solve. It looks pretty complicated, but again, we can do this little by little. There's the equation, so now we need to simplify, multiply things together, and here you have to be careful because you see we have the 3780 times the quantity x minus 40. And we have to remember that when you have a situation like this, you need to multiply the 3780 by the x and by the minus 40, according to the distributive law of algebra. We've done this now. The 2250 times 40 is 890. Then we have multiplying the 3780 by x, that's the next term. Then 3780 by minus 40 is the third term on the right. Let's simplify some more. When we've done the multiplication, we see that on the right we have the 890, the 37.80x. Then when we multiply 3780 by 40, we get 1512. Now we continue and we take 890 minus 1512, combine those two to get minus 622. We still have to simplify some more on this. Let's write this on a new slide so we have a little bit more room. And the next step is we add 622 to both sides of that equation and then do the corresponding math. When we do that, we get 1795.50 is equal to 37.80x. The next step, I'm going to give you a second. What should I do next? Divide both sides of that equation by 3780. When I do that and do the math, I find that the total time I worked, remember that's what x was, is 47.5 hours. Remember what I said though, how did they want this answer? They wanted the answer not only in tenths of hours, they want it in hours and minutes. So we need to look at that 0.5 hours and change that to minutes. Fortunately for us, 0.5 hours is relatively easy to calculate. Remember, 0.5 is 1/2, so that represents a half of an hour. If I multiply 0.5 of an hour by 60 minutes, I find that's 30 minutes. So what she's actually worked for that week then is going to be 47 hours and 30 minutes. Of course, I can check this. You can always check if you have an equation by taking the value you get, 47.5 for x, substituting that back in the equation and seeing if that works out to the number on the left-hand side of the equation. When I do the math with this, work it out step by step, I find that I have the same thing on the left and right side of the equation, and at this point I can pat myself on the back for having been able to do a fairly complex problem. Let's look at another one that involves two unknowns. These two unknown ones are at least fun because they're interesting. They give you something to sink your teeth into. The total receipts of a basketball game is $1,400, and they sold a total of 788 tickets. Adults pay more than students, and we want to know how many tickets of each kind were sold. There are adult tickets and student tickets, and what we know is the total number for both. let's look for the information. There's the total receipts for 788 tickets. We know what adults pay, we know what students pay, and we have two unknowns here: how many tickets of each kind. Let's summarize the information: the total receipts, the number of tickets, the two different kinds of tickets. What we're asked is how many student tickets, how many adult tickets. We know we've sold a total of 788, and we have divided between student and adult tickets. We just don't know how many of each, and that's what we're looking for. Let's continue picking this problem apart. We'll have T tickets, and we'll say that is the number of tickets sold to students. Then if there are that many tickets sold to students, whatever is remaining of the 788 must be sold to adults. So the total received is the student money plus the adult money. Now the student money, we know the total is $1,400. Then the student money must be the price paid by each student times the number of students. The adult money is the price paid by each adult times the number of adults. And the trick here is to relate the number of adults to the number of students, because we know the total, and if we have T tickets sold to students, how many tickets are left? It's the total minus those sold to the students. Now we have an equation, and once you have an equation, of course, that's the easy part. Getting to this part and reasoning this out, as I did here, is always acknowledged as the hardest part of solving a word problem. Well, let's go on with the easy part. We have the equation. Now we need to do the math associated with the equation, and let's simplify. We need to operate on the right. Now remember, just as we had in the previous problem, we need to multiply that number on the outside of the brackets by both terms inside the brackets. We've done that here in the second step, so I have 1,400 is equal to 1.25t plus 250 times 788 minus 250 times t. Let's continue to do the math. I do that multiplication, but I see I have two quantities with t on the right-hand side. I can combine those and get that. Let me now get rid of the 1970 on both sides of the equation, and I get minus 570 is equal to minus 125t. Let's start there. But now, since we have a negative on both sides, let me just take the opposite of both sides to make those positive, get rid of those annoying negatives there, and divide both sides of the equation by 125, and I find the number of tickets sold to students is 456. How do I get the adult tickets? It's 788. The total number of tickets minus those sold, 322. And so, just to check, I have that is the equation. I put in what I get for the T, the number of tickets sold to the students, do the math, and I find out that 1,400 equals 1,400, and I'm good. I've done this problem correctly. Let's now look at a problem using some simple geometry. How much tape must be used to connect rectangles of cardboard to make the box below? And we know that if I wanted to make a box, one piece of tape overlaps two sides. There's the box, there are the dimensions of the box. What are we asked for? How many pieces, how much total tape must I hook up to make that box work, make the thing into a box, and, well, how much tape? We're given the size of the box. There's the diagram of the box given in centimeters. Remember, a centimeter is about 1/3 of an inch. And we want to know how much tape I need total. Now, this is one where we're going to have to ask how many common edges and what size we have. There's the front of the box, and let's see the hidden edges. We can color those edges of tape, and we see we're going to need 4 pieces of 3 different lengths. Let's just add up the total tape. There's that piece, 4 pieces, that 4 pieces, that 4 pieces. Let's just sum all of those things up and finally get the total number of centimeters of tape.